have few slides on that. Let me recall a little bit about the last class, right? So we were doing addition of nucleophile and electrophile on the double bond between the carbons, right? So you had alkene pi bond. So you're gonna add different group to that. So you're gonna have the product, right? So if you have the addition of HX, hydrogen halide. So the question is, in which carbon the hydrogen gonna go? In which carbon the halogen gonna go? So based on that, you're gonna have the Markovnikovs or anti-Markovnikovs, right? So for the first one, if you do not have peroxide, if you do not have any source that's gonna produce radical, so that's gonna go to Markovnikov's route. If you have something with the reagent, so you're gonna have HX over there. On top of that, if you have anything like peroxide, hydrogen peroxide, or any other reagent that's gonna produce radical, so then you're gonna have the entire Markovnikovs. Okay. After that, we went through the rearrangement. So for both Markovnikovs or anti-Markovnikovs, if you have any carbocation, and then in its neighbor, if you have any higher degree carbon, so the carbocation gonna want to be higher degree carbocation, because more degree carbocation you have, more stable it's gonna be. And then you're gonna have the group attached to that, right? So for example, if you see over here, so initially you're gonna have the carbocation over here, right? So this is 2 degree carbocation. So if you have any neighboring carbon, then you're gonna have more than that, which is 3 degree. If you have any condition like that, then it's gonna go there. So the nucleophile will not be attached to this carbon. So instead, what you're gonna have is, this gonna go to the next carbon over here, and then one group can migrate to the position you had carbocation before, right? So then you're gonna have something like this. So now this is 3 degree, right? So the carbocation went from 2 degree to 3 degree. Now you're gonna have the nucleophile attached to that carbon. This is called rearrangement, right? Sometimes the hydrogen can facilitate that, or the hydrogen can move to the next carbon. Sometimes even methyl, because it is a small group, right? So methyl can move there. If you have the larger group like propyl, butyl, it does not. If you have the small groups, they're gonna move. Okay? So that's the just recap of the last class. Now, our next reaction is gonna be, what if you do not wanna have the rearrangement? So you wanna add the nucleophile in the carbon that has the plus charge in it, even if it is a lower degree. So you don't have the rearrangement of the carbocation to the other carbon, right? So this reaction is for that. So it's gonna prevent any rearrangement in the Markovnikovs. That is not for anti-Markovnikovs. So we're gonna see Markovnikovs first, and then we're gonna also see the anti after this. But this is only for the Markovnikovs product you have. Remember this, and it's gonna prevent the rearrangement on that. Okay. So for that, you need to have the specific reagent, which is this one. So mercury acetate, that's the name of that. And then with that, you're gonna have these two. So these two are gonna go together. So why these two gonna go together? So the mercury acetate gonna prevent the rearrangement, and then you're gonna add the nucleophile there. After that, you wanna take the mercury acetate out from the product, so you're gonna have the desired product there. So the sodium borohydride, this one, is to take the mercury acetate out from the product. So these two are gonna go together. Okay? If you see these, then you're gonna remember that you will not have any rearrangement. So you're gonna have the product like Markovnikov's. So let's see over here. This is alkene, right? So if you do not have this, then what product do you expect? So I'm gonna write over here. So for that, what you're gonna have is, let's say you're gonna add H2O, right? H2O in presence of acid, so you need catalyst for that, right? So let me just write H plus. So this is acid. H plus represents HCl, H2SO4, HNO3, whatever you have there, right? This is the hydrogen donor. So now if you have that, what's gonna happen is you're gonna have this, and then hydrogen is gonna be added over here. So I gotta put that hydrogen. So red hydrogen is going to be over here from the water, right? So you have the H and OS. So this is the hydrogen I'm writing over here. So this is going to be bonded there, right? And then you're going to have the plus charge on that carbocation, okay? So if you have just that without the mercury acetate, then what are you going to have? This is 2 degree carbocation. And then this is going to go over here, so it's going to be 3 degree carbocation, right? So you have the hydrogen there, 1 hydrogen, right? So carbonate tetravalent, you have 1 hydrogen over here. So this hydrogen is going to go over here, and then the plus charge is going to go over here. So you have the rearrangement if you don't have mercury acetate, okay? And then finally, what you're going to do for the product? So product going to be this one. So you're gonna have OH bonded over here, and then you're gonna have the hydrogen bonded there. So that's gonna be your product. Okay? So this is normal without preventing the rearrangement. So this is the product to be expected. Right? But if you have this, if you have this mercury acetate, then this expected product will not be formed. Okay? Instead, what you're going to do is you're going to add this OH in the carbocation. You're going to add over here without the rearrangement. That's the reason why you have OH over there. Okay? Without the rearrangement. So this is called the oxymercuration reduction. So the oxidation reduction is going to be in next chapter. We're going to go in detail how to define that, everything. Okay? That's the name. So the important thing is remember the reagent. Okay? So if you see any reaction, alkene reaction with the mercury acetate and the sodium borohydride, that means you need to remember it's going to prevent the rearrangement. Okay? You don't shift the carbocation to the higher degree carbon. You're going to keep whatever it is without any rearrangement. Alright? So the mechanism for that we're going to see in next chapter. It's going to come again and again in many reactions. Okay? So we're going to deal later. Okay? Good? So here only you're going to remember that if you have alkene, say hydrogenation for example, if you have the mercury acetate and sodium borohydride together as a reagent, you will not have any rearrangement. That's the point. Okay? Alright, so now the next one. So hydroboration, that's the name. You're gonna add BH3. So this reagent, what's gonna happen is you're gonna have the anti-Markovnikov's product. So you're gonna have this, right? Also, it's gonna prevent the rearrangement like before. So these are the two rearrangements. Remember that. So hydroboration is gonna prevent the rearrangement, but you're gonna have the anti-Markovnikov's product. So the before one, it is the Markovnikov's product. There is difference. Okay. So what it's gonna do is BH3. So boron is trivalent, right? So you have the B, and then H, and then H, and then H. You have 3 bonds, right? So the hydrogen is going to be replaced by whatever alkene you have there. So you're going to connect the anti-carbon you have to the boron. So this is for one hydrogen, this is for the another hydrogen, and this is for the another hydrogen. So first, simply, whatever alkene you have, you're going to connect that to the boron. So 3 is the maximum one. You're going to have that. After that, what you're going to do is you're going to do the actual nucleophile substitution with that group. So you're going to have the OH for N carbon. So this carbon, and this carbon. These are the end, right? So you have 3 of those. So you're going to have the 3 product, right? So that means 1 mole of reagent is going to give 3 moles of product, right? Because you're going to have the 3 alkene attached to 1 reagent. And you're going to have the product based on that. Okay? So now this is anti-Markovnikov's, right? If you think Markovnikov, then the hydrogen should be over here, and then OH should be over here, right? Here you have the opposite, because boron gonna seal that initial attachment to the hydrogen, so hydrogen has to go to the next carbon after that. So it is anti, right? So that's the reaction you have. So this is the step to show the same thing, right? Now if you summarize everything, so for the acid catalyzed, this is just the normal reaction with Markovnikov's addition. You're going to follow that. So you're going to have the rearrangement if you have any condition in the reaction, right? If you do the oxymercuration, then it's going to prevent the rearrangement. So it's going to be based on Markovnikov's. If you have the hydroboration, then it's going to be based on anti-Markovnikov's addition. Okay? So that's the summary of the addition of water. You're going to have the alcohol with that. Right? Confused? I know you're a little bit confused. So you need to practice a little bit. Okay, so there is no other way. So for example, how to know the reagent, I'm going to give that. So just you need to practice a little bit. Okay? Alright, so the 2 important things you must remember is peroxide. If you have hydrogen peroxide, it's going to give the anti-Markovnikov's product. Remember that. Okay? And then if you have the mercury acetate, then it's going to prevent the rearrangement. It's going to give the Markovnikov's product. Okay? These 2. If you remember these 2, then all they're going to be just a regular. That'll be easier to follow. Alright? Any question on this before I go to next chapter? Alright, then I gotta go to the next one. So we're gonna deal with oxidation reduction, right? So now you're gonna recall some of the concepts you went through in Gen Chem 2, right? You have the oxidation, reduction, electrochemical series, you have the electrode potential table, something like that. Then you're going to compare the values and then see which one is going to be oxidized, which one is going to be reduced, like that. You also did the lab for that, right? So, now, let me give very simple examples. You don't need to remember all those data, but the concept, okay? So the very classical example of redox is, say you have, not yet, let's say you have NaCl, right? So you have sodium, and then you have Cl2, and then you're going to have NaCl formation. Right? Very simple classical example. Even from Genchem 1, right? You see that example. So now, is this redox reaction or not? So for that, what you did, so for the uncombined atom, you're going to have the 0 oxidation number, right? Same for chlorine, you're going to have 0. And then for the combined state, one going to lose electron, other going to gain electron, right? So you can have the Na plus Cl minus combined together, right? These are ions. So now you're going to see, you're going to compare the number. So sodium 0, 2 plus 1, that means the loss of electrons, right? And then for the chlorine, 0 to minus, going to be gain of electron, right? So the loss of electron is oxidation. So you're going to write this as oxidation. And then the gain of electron is going to be reduction. You're going to write reduction for that. So this is standard definition. Okay, so sometimes you can follow the classical. Say, for example, if you recall Genchem lab, you did magnesium plus oxygen. You have the MgO, the empirical formula, right? You did that. So if you have like this, you don't need to worry about the number. Doesn't matter what number you have. This is oxygen addition to the magnesium, so you can have the magnesium oxide, right? If you have the oxygen addition, this is oxidation, always. This is always. There is no exclusion at all, right? So if you have any compound, if you add oxygen in that, this reaction is oxidation, right? Of course, you're going to have the reduction part, but the center that you add oxygen in, going to be the oxidation, right? And then the other one, say for example, magnesium, you're going to add hydrogen on that, you're going to make the hydride, MgS2 like that. If you add hydrogen, this is reduction. This is the classical old definition of oxidation and reduction, right? So these two, oxygen and hydrogen addition, I'm not saying this is wrong, but these have limitations, okay? So not all the time you're going to add hydrogen or oxygen. Say you're going to add halogen, right? Then how to define based on that? You cannot, right? You have the limitations. So that's the reason why we're going to stick with this on the basis of electron. So this is general for all types of reactions. So you're going to stick with the electron, whether it is lost or gain, and then you're going to define. Yep.
So is this how there are different definitions for acids, kind of thing?
Yeah, you can correlate that.
Like that? Okay.
Yeah, so when you have, you see, you're going to ionize, you're going to have the charge on that. So you can have +1, -1, +2, right?
But like how you have the Brown's 3 definition of acid.
Oh no, this is a little bit different. So this doesn't say acid or base anything, right? So you have different class of reactions, like how you're gonna classify that, right? So you have the acid-base reaction, you're gonna have the oxidation reduction reaction, you're gonna have the displacement combination, all different types of criteria to categorize that. So this is based on the electrons gain or loss. So that's going to be the oxidation reduction. I'm not saying that in acid-base reaction you will not have oxidation. You can,
Yeah.
right? So there are different types of classification.
Okay. Thank you.
So now, let's see. The first thing is, for organic molecule, it is a little bit complicated. So you don't have the simple molecule like NaCl, MgCl2, like that, right? So you have many atoms in the molecule. So you're going to have many carbon atoms, many hydrogen atoms, many non-carbon hydrogen atoms over there. So you have many atom centers there, right? So you're going to see each and every atom in the molecule, and then you're going to conclude based on plus or minus you have in the molecule, right? So a little bit complicated. So to simplify that, we're going to follow with the oxidation number. So this is the first thing you're going to calculate. At the beginning, you're going to calculate. After that, when you are used to, you can calculate on your head. So you can just like figure out which carbon going to have which charge, right? But at the beginning, we need to calculate that. So what is oxidation number? So based on the Genchem concept, any charge you have on the atom center is oxidation number. Okay, if it is simple, like monoatomic or diatomic, simple center, right? But here it's going to be a little bit harder. So you have many atoms there. So we're going to calculate. Okay, so how to calculate? This is the formula you're going to use. So the oxidation number is equal to, remember, it is not for molecule, it is for the atom center, each atom. Okay, so the oxidation number of a given atom is the valence electron you have for that, and then after the reaction, how many electrons it gonna have, right? So you can say number of electron assigned, or you're gonna say this. So number of electrons owned. So how many is gonna own? So that probably that will be easy to remember, right? So the valence electrons are fixed at the beginning. This is gonna be in the uncombined form. So you can see that in the periodic table. So you don't need to memorize anything, right? So see the periodic table, take the outermost energy cell you have, count how many electrons you have there, that's the valence cell, valence electrons, okay? Now for the second part, how many electrons owned, this is after the reaction. So see the bond type and then count how many electrons you have there for that atom. Okay? So for that, you're gonna see this. So if you have the lone pair electron, you're gonna count that. Okay? If you have the covalent bond, then the more electronegative atom, that's gonna hold all the bonded electrons. So the less electronegative atom does not have any electron owned on that. Okay, so remember these two. So now apply this. For example, in this molecule, let's say CO2 for example, the simplest one. So let's calculate for the carbon. Okay, so calculate the oxidation number for this carbon in CO2. So you're gonna apply the formula. Okay, so oxidation number gonna be equal to, you're gonna write the valence electron of carbon first, right? So what's gonna be that? Number of valence electrons. 2, 3, 4, 5, 6. What do you think? Okay, I'm gonna draw over here So carbon is the common, you're gonna have carbon in all hydrocarbon, right? So at least you must know for the carbon, and then for other non-carbon like oxygen, nitrogen, halogen, these are common in the organic molecule, right? So remember those. So for the carbon, let's say this is N1, N2, okay? So you can see the number in the periodic table that is called atomic number on top of the symbol. Right? So what do you see there? 6. Right? If you see the periodic table, you're going to see number 6 for that. So you're going to see normally like that. So 6 is going to be atomic number. So that means this is uncombined normal form. You're going to have these 6 total electrons in the carbon. Right? So now you're going to feel that. So for the first, you're going to feel 2 electrons, and then you're going to feel the remaining. You're going to have 4 over here. So N1 is going to be the 4 cell. You're going to discard that. Just take the outermost cell you have. So in this case, N2 is the outermost cell you have. Count how many electrons you have there. 4. So that's why you're going to write 4 over here. So 4 is the valence electrons for the carbon, right? So now the next thing is determine how many electrons carbon gonna own after the reaction, right? So after the reaction, it's gonna give this one, CO2, right? So carbon 4 gonna be just the carbon before reacting with the oxygen. So now you have CO2. So now you're going to count the owned electrons. So what do you think? So here, how the bonds are formed? So the carbon has 4. So these 4 dots are the electrons of carbon. And then it is shared with the oxygen. So I'm going to write the green dot for the bond. So you have the 4 dots for the 4 bonds, right? Like that. So the blue and the red gonna give 1 bond, and the second blue and red pair gonna give second bond, and so on. You have 4 bonds there, right? So now the question is, what number should I write as the electrons owned by carbon after the reaction? I mean in CO2. So remember this over here. The more electronegative atom owns both bonded electrons in the bond. Okay? So for 1 bond, you have 2, right? So oxygen gonna be the more electronegative, so both gonna be with the oxygen. So carbon does not have any of the bonded. The same on the other side. So oxygen gonna keep that, so carbon does not have any. So how many? 0. It does not. Right? So if you have the molecule, like say for example this one, so you have the carbon-carbon, so then you're going to divide 1-1 between these carbons because both have the same electronegativity. Right? So 2 electrons in 1 bond going to be divided equally between 2 carbon atoms because they have the same electronegativity value. Right? But if you have something like that, like C and H, how do you divide these 2 electrons, the bonded electrons? So the carbon has more electronegative value than hydrogen. So both electrons are going to go to the carbon, not to the hydrogen. That's how you're going to distribute, right? So see the bond over there. Compare which is more electronegative atom you have. So both the bonded electrons gonna go to that more electronegative atom. Okay? For example, CH bond, both electrons are going to go to carbon. For CC bond, since they are equal, you're going to do half-half, 1 electron each. If you have CO bond, then carbon will not have any electron, both going to go to oxygen, like CO2 in this case. Okay? So now what is the oxidation number? 4, right? That's why you're going to write +4 over here. Okay? So now you can calculate for the oxygen, right? You can do the same thing. So what's going to be for the oxidation state for oxygen? So what's going to be the valence electron? So oxygen is next to nitrogen, right? So carbon and nitrogen and then oxygen. So 2 more than carbon. So it's going to be 6. And then now you're going to subtract the electrons owned. So what's going to be that? So both bonded electrons are going to be for the oxygen, right? So you have 2 for one bond, 2 for another bond. So 4 electrons from 2 bonds are going to be owned by oxygen. Okay? And then you're going to add the lone pair if you have there. This is already on oxygen, right? So you're going to have 1, 2, 3, 4, 5, 6, 7, 8. So you're going to do 8 over there. So -2. That's why you have -2 number for that. Okay, so that's how you're going to do math for each and every atom. Then you're going to see whether it is redox reaction or not. Okay, so for this one, it is redox reaction, right? Because carbon at the beginning going to have the 0, and then now it has the +4, change in number. Okay. So now I need to calculate for the second and third, right? Can I do it? The second and third molecule. Can you calculate for the carbon in the second molecule? So what is going to be the value? In ethene, what is going to be the oxidation state of carbon? -2. You have 2, 4, 5, 6. Yes. You're going to have -2, right? So 4 minus 6 is going to be -2. So you're going to do like that, right? Good. Any question on that? Yep. Acetate? Which one? This one? Okay.
Specifically just the split of either 1 and 2.
Let me see. You mean for this one? Okay. So for that, so you mean this carbon, right? Okay. So this carbon, let me calculate the carbon. There are 3 hydrogen in it, right? So you're going to do the same formula. So for that carbon, I'm going to write over here. So what is the valence electron? Carbon going to have always same 4, right? And then what is going to be the electrons owned? So you have the bond between carbon-carbon, so you're going to split half-half. So you have 1 for that, 1 for carbon-carbon bond, okay? And then you're going to have 2 for CS bond. So 1 plus 2 plus 2 plus 2, right? So 3 times 2 is going to be 6, and then you have 1 from carbon-carbon bond, so 7, okay? So I'm going to do 7 over here, so -3, right? So that's why you have -3 over there, okay? So same formula, just be careful, like count all the non-bonded electrons there. So that's going to be for the specific atom property, Piper property, right? And then if you have the shared one, then which one is stronger to grab it? So more electronegative atom, that's going to take both shared electrons. Count all and then put in the formula. Yep.
And carbon 2 only has 1 because
Yes, so whatever bond you have with the oxygen, it is not owned by carbon. Both gonna go to oxygen. Oxygen is more electronegative, so you don't count those two bonded with oxygen. Right? Yep. Good? Alright, now you can calculate, right? Alright. So now, let's see how to answer for any reaction, whether it is oxidation or reduction or redox. So normally redox reaction can have two parts there, or it is not redox reaction. So how to distinguish that, right? So let's see one example. This one A. So reaction is given. You don't have just the molecule, you have the complete reaction. So this is reaction, right? So halogenation of alkane. So we see the reaction before, right? Remember the chain mechanism, the radical mechanism? So this is for that reaction, right? Halogenation. So you have this reaction. So now you gotta answer that whether it is redox reaction or not. Okay? So how to answer that? You gotta calculate the oxidation number and then compare between the atoms. So for that, let's do for the carbon before the reaction. So this is before reaction. And then the carbon you have over here is after reaction. If you have the same oxidation number before and after the reaction, this is not redox reaction. Okay? If you have the different oxidation number before and after the reaction, then it is redox reaction. That's how you can answer. Alright? So now for this one, use the same formula. So the valence electron is going to be 4, like before. And then you're going to subtract with the electrons owned by that. So how many electrons owned? So carbon is more electronegative than hydrogen, so both going to go to carbon, right? So you're going to count 2 for that, another 2 for the next bond, and then another 2. So you have 4 bonds. 4 times 2 going to be 8. So you're going to do 8 over here. So going to be minus 4, right? So you have the minus 4 oxidation state for the carbon before halogenation, right? And then you're going to count after halogenation. So now you're going to have bromine there. So bromine is more electronegative than carbon, so you don't count that bond. So the CBr electron is going to go to the bromine. Carbon doesn't own that. Okay? So then how many? 2, 4, 6. So you had 4 before, now it is 6. So minus 2. So you have the minus 2 oxidation state. So now you have minus 4 to minus 2. So it is gain of electron or loss of electron. So the more negative is gain, less negative is loss of electron. Electron is negative charge entity, right? So this is loss of electron, right? Loss of electrons. So what is loss of electron? It is oxidation or reduction?
Oxidation.
Oxidation. That's why the carbon is oxidized. Okay, so don't be confused with the oxidation and the oxidizing agent. That's a different thing. Remember, then came one, reducing agent and oxidizing agent, right? So carbon is oxidized means the reducing agent or oxidizing agent isn't the same thing. So oxidizing agent is going to be the next molecule that's going to facilitate for the oxidation. Okay, that is bromine, right? And then let's see bromine, you have 0 at the beginning, so 0 charge, this is the molecule. So now you're going to have -1, so gain of electron, so this is reduction, right? So this is reduced. And hydrogen, you have the +1 at the beginning, +1, after that, no change on hydrogen, okay? So here you have two reactions. One reaction is oxidation involving the carbon-carbon. Other is reduction involving the bromine-bromine. So you have the both part in this reaction. So it is redox reaction. That's how you can answer it. Right? Now it doesn't mean that all gonna be the redox reaction. It may not be. Okay? So let's see the second one. This reaction. The second reaction. So it may not be, or maybe we can count, right? So carbon, so you have the same electronegativity, so you're going to have the equal owning for these central carbon-carbon bonds. Okay? So 4 for the carbon minus, you have 2, and then you have 1, 2. So 1 for one bond, half. Okay? So you have 6. So that means -2. So you have -2 for the carbon. Same for the other one, right? And then after the reaction, you have, you're going to count both for hydrogen, both for hydrogen, both for hydrogen. So you're going to do half for that. So for that carbon, 4 minus 2, 4, 6, 7, right? So going to be -3. So you have -3 charge. Okay? What about the other one? So other one you have the oxygen, so you don't count that. So oxygen going to take all the electrons that is shared. So now for this carbon, you're going to have 4 minus 1, 2, 3, 4, 5. So you're going to have 5. So -1. So you have -1 over here. Okay. So now what's going to be the total for the carbon? Take one atom at a time, okay? So you have 2 on the left side, both have 2, -2. So this is the total carbon you have on the left side, okay? Right side, you have 1 with -3, other with -1. So what's going to be the total? On the left side, you have -4 total, because you have 2 with -2. So the sum going to be -4, right? And then on the right side, -3 and -1 going to be -4. So -4 on the left side, -4 on the right side. So essentially, you don't have any change, right? And then the charge on the oxygen, you have -2, this is same on both sides. Hydrogen, you have +1, +1, so you have same. So virtually, there is no net change in charge or the oxidation state, right? You have the same oxidation state on the left side. You have the same oxidation state on the right side. So it doesn't change. That means it is not redox reaction. Okay? So that's how you're gonna classify. Sometimes it is very confusing. If you see only one carbon center, you may see the change. So take all the carbons you have in the reactant, all the carbons you have on the product, and then compare the total overall change in oxidation state. If you have 2 carbons, add the charge on 2 carbons on the left, and add the charges on the 2 carbons on the right, and then see the value, net value you have. If you have the same net value, no change. If you have the difference, then yes, you have the change. Okay? That's how you define it. Right? Is it confusing or not? It is actually, it is confusing. So if you get it, that's good. Right? Alright, so now we're gonna go to the reaction after that. Okay, so now we know how to define the oxidation number, how to distinguish oxidation reduction reaction. Then we're gonna go to the actual reaction for the alkene, because this chapter is for whole alkene reactions. We'll not see other, but gonna be the alkene reactions. That's gonna involve oxidation and reduction. Okay? So that's the reaction we're gonna be on. So the first reaction is gonna be halogenation. So we already see the halogenation of alkane. So now we're gonna see for alkene. Okay? Essentially gonna be the same thing. So you're gonna add halogen on the carbon. Right? That's the halogenation. So you can see halogenation, you can see halogen addition. You can call that. So you're gonna add halogen on the alkene, right? So which part you're gonna add? It is very obvious, right? Pi bond is the one you focus over there. So the pi bond is going to be the reactive sector, so you're going to add there. So you're going to break the pi bond and then you're going to make the bond with the halogen in it. That's why it is called halogenation. Okay? So now let's do it. So you have the carbon-carbon pi bond, you have the bromine. So what you're going to do is, you're going to add one bromine to one carbon and another bromine to another carbon, so that both carbon are going to be tetravalent like before. Alright? So that's how you're going to make the bond. So the product going to be dihalide. You can also call that bicinol because next to. So that term I'm going to refer to, you have the bromine on one carbon and the another bromine to the next carbon to that. If you have just right next to two halogen bonded to the carbon, this is called a bicinol dihalide. Okay? So you can have that because you are breaking the double bond. So for the double bond, you're going to have the pi electron between the neighbors. So one going to be bonded to one carbon with the double bond, other going to be to the other carbon with the same double bond. So it's going to be always bicinol dihalide. Right? If you have the diene, triene, tetraene, then you're going to have the difference. But if it's simple alkene, you're going to have always bicinol dihalide. That's the product. So now you know the reason why, right? So pi bond. So two neighbors are shared electrons to form the pi bond. So you're going to add two bromines on the neighbors next to each other. That's the bicinol. Okay. So this is the product. So now you can calculate the oxidation number, right? So if you're going to say whether it is oxidized or not, you can calculate it. So for this one on the left, it is symmetric molecule, so both carbon gonna have the same charge when it is symmetric, if you have the same atoms there. So you have 4 at the beginning, and then how many?
6.
So you're gonna break half for 2 carbons because they have the same electronegativity values, right? So you're gonna have the 2 from hydrogen, 2 from here, 4, 5, 6. So you're gonna have 6 and then minus 2. So you have minus 2 for one carbon, minus 2 for other carbon. That's the oxidation state you have there. Okay? And then now in the product, you're going to see for the same carbon atoms you have. So now bromine, you don't count that because bromine is more electronegative than carbon. Carbon doesn't own anything for that bond. Okay? So now you have the carbon-carbon, you're going to do half-half. So you're going to have 1 for the carbon-carbon bond, and then 2 for the hydrogen, 2 for the hydrogen, so 2, 2, 4, 5. You're going to do 4 minus 5, So you have the -1 there. Okay? So now see the change. So how many on the left side? 2, 2, 4, right? So -4 on the left side. And then how many on the right side? You have -1, -1, -2. So you have the change there. Right? So change means it is losing the electrons. The carbon lost 2 electrons and then went from -4 to -2. So this is oxidation. Right? So that's how I can answer. Alright?